Hi everyone, so right now we're on page number 323 of the textbook on radioactivity. We're looking at 17.2. Now we already have covered a couple of parts for nuclear decay, nuclear decay, but I'm going to go through it again just so that everybody can be clear. Alright, now let's start first with the definition of what is nuclear decay. The idea of nuclear decay is that something is happening to this atomic nucleus, and this atomic nucleus is unstable. So what happens when it's unstable? It is going to be losing two things. It's going to lose, one, energy by emission of electromagnetic radiation or particles. So I could lose this or I could lose this. Two possible things I can lose. Remember, it must be something that's random, and that means I can't tell when it's going to happen, but I know it will. I do not know where it will go. I do not know when it will happen. So once again, random process that happens to the unstable atomic nucleus, right? And when that happens, it's going to lose energy, right? It's not just losing particles and radiation, it's losing energy by that emission of one, a particle or particles, or the other way is emission of EM radiation, okay? Now we have looked at this before, and we've also learned this in terms of electromagnetic spectrum. Now let's look into the three possible things. So we did say that I could lose particles or through EM radiation. So what are those things? So what are these emissions? So now we look into the three types of nuclear emissions, and we're comparing alpha, beta, and gamma. And when we look at these three, we're going to compare their relative ionizing effect and their relative penetrating ability. But of course, before I go on, we need to understand what I mean by ionizing, correct? When I talk about ionizing, I mean that this radiation, right, alpha, beta, gamma, when I send this radiation across, right, and it hits an atom, this is able to knock off electrons from that atom, and that atom becomes an ion, becomes charged, right? So it really comes down to something like this, okay? Let's say this is a drawing representing an atom. Of course, it doesn't fully represent an atom, but you can roughly see protons, neutrons, electrons, right? So let's say I send through a certain emission, okay? Let's say it's a gamma wave, okay? I'm going to send, how should I draw a gamma wave? Gamma wave is it's a radiation, so I should draw a wave, right? So, right? Let's say that is going to go over here, and it hits it, bam, it's going to knock off the electron, and now this atom, right, is going to miss one electron. This becomes an ion because it's charged, right? So these three, what is the ability to ionize, to knock off these electrons? Okay, so that's what ionizing really means, okay? And you can look again at page number 325 of your textbook, page 325. Read again what ionization means, okay? So ionizing effect of this radiation, ionizing radiation. Now, penetrating ability just means how far can I get through, right? What do I need to block this radiation? If I am worried about being exposed to all of these different radiations, what can I use to block myself such that it cannot get through to me? Penetrating means going through. What stops it? Okay, so alpha, beta, gamma. These are the relative ionizing effects and relative penetrating ability. Alright, so alpha has the highest ionizing effect, which means once it comes into contact with an atom, right, bam, it's really going to knock off electrons very easily, but it doesn't get very far. It has the least penetrating ability. It's stopped by something as simple as just a few pieces of paper or aluminium foil, right? Stopped by paper. Okay, so the way I remember this is like alpha, right, basically has the idea of there's a very high splash damage, right, but doesn't get far, right? It's coming to gamma, right? The damage it has for just 1 point is very low, but it's able to get through beyond. So it's kind of like Moskov, okay? When you shoot, right, this will be able to penetrate to the next target and go further through, right? So while it doesn't knock off a lot of electrons, it's able to go much further and much deeper than everything else. That's why you have this picture in your textbook. So I wonder if you actually know Moskov. Most of us should, right? Mobile Legends, you should know. Okay, anyway, so if you look at this over here, An alpha particle is able to really cause a lot of damage, but this picture just talks about the penetrating ability. Okay, you can't really tell much of its ionization power based on this diagram, but this diagram talks about its penetrating ability. Alpha stopped by just like a piece of paper. Beta is able to go through the piece of paper, but it's stopped by a few millimeters of thick, few millimeters thick aluminium. It's not very thick, okay, sorry. But gamma rays is able to go all through the paper and aluminium, but you gotta have a few cm of thick lead. I can say no thick. You have the few cm of lead for it to be blocked. So what is the best way to block yourself from all radiation? Well, technically you need to have lead, because with lead, alpha definitely will get through, beta will get through, gamma will get through. But if you're just concerned about alpha radiation, right? Alpha particle radiation, right? You just have paper and you're safe already. Okay, so this is the 3 different types of nuclear emissions. So now the next part is really about counting it. That's where you need to understand how you measure all of this radiation. Because take note, right, that even though there are these 3 different types of nuclear emissions, alpha, beta, and gamma. Oh, I need to mention one more thing. Remember that we say that it's a random process where the unstable atomic nucleus loses energy by emission of particles and EM radiation, right? Now, I know that this is an EM radiation, correct? Which means, right, these two, right, are literally particles. Now, what particles are these actually? Well, the alpha particle is very, very close to, very similar to, where's my dot? Okay, pen's working. Very similar to helium nucleus, where you actually see 4,2 helium. Okay, but it's not helium. What you see in a textbook is not 4,2 helium. It says 4,2 alpha. Right? It has 2 protons and 2 neutrons. 2 protons, right? This is 4 over here, right? So that means there's 2 protons and 2 neutrons. This is the actual alpha particle, right? If there's an alpha decay, then it emits an alpha particle, right? That's just identical to helium. What about beta? If I have a beta decay, what actually comes out, right, is really a fast-moving electron, right? So if I have to draw it out, right, this fast-moving electron will be beta, right? Does it make sense? Right? It's not a proton, it's an electron. So that's how I'm going to notate it. Don't have to worry too much about this notation. Just know that this is actually a electron that's being ejected from a radioactive nucleus. Now, of course, well, this over here, I think it's pretty obvious, right? It's just EM radiation. So something similar to what I drew over here. Okay? The radiation that you have seen before are, well, what we did in the previous chapter, remember? Gamma, X-ray, ultraviolet, visible, infrared, microwave, and radio waves. Now, as we have said before, right, those with the highest energy is going to be these 3 typically. Okay, these would have radiation that are ionizing. Okay, so from here downwards over here, right, these are typically going to be the non-ionizing radiation. Now, to be clear, right, we have radiation from a couple of sources. Not just the artificial sources like X-rays and even like those waste products from nuclear power stations. We have natural sources that still actually give us radiation. So let me take a photo of that. All of these contribute to what we know as my background radiation, right? Background radiation just comes with that is all that nuclear radiation, right, in the environment that we get, that is not from anything that I deliberately introduced. It means I'm not going to put this thing which is highly radioactive. No, it's just background radiation from all these different sources, artificial and natural sources. That means wherever you are, right, you are subjected to some amount of radiation, right? So there's a safe amount we can and there's an unsafe amount we have. So how do you know that we're safe? Well, that's where you need to do measuring of ionizing nuclear radiation. Okay, so from here we are moving on to the next part, measuring ionizing nuclear radiation. Now, if I'm trying to measure something, it means that I also will require SI unit. correct? If I want to measure length, I need to be able to have meters, time, seconds one. How do I measure nuclear radiation? I would need to have a device or instrument to measure it, and I need a unit, and I have both. The instrument we use is a Geiger-Müller or a GM counter, and the unit we're going to use is becquerel or just BQ, right? What is BQ? Well, one becquerel, it just means, right, one disintegration per second. Now, try to recall, right, that we talk about disintegration, right, we are talking about this unstable atomic nucleus losing energy by emission, right? So it's starting to like, right, disintegrate, right? It's going to break up, it's going to decay. So one disintegration per second, right? So that's how much ionizing radiation is released when a radioactive atom, it spontaneously by itself, right, emits nuclear radiation due to decay, right? So typically comes down to this, it's going to decay, right? It's going to emit EM radiation. So how much ionizing radiation? Well, I can find that in the disintegrations per second, all right? Okay, so typically what you're going to do, right, is if I want to measure this background radiation in the first place, right, I'm going to need a stopwatch, because if it's per second, well, that means I got to time it, right? So what usually you do, right, is that to measure background radiation, there's 4 steps, and I'm going to take a photo of that right now. Oh wow, that's so ugly. Never mind lah. Right, so we take away all those things which are clearly radioactive, and I just want to find out background radiation. So I'll start my counter, right, the thing which I'm measuring with, and I'll start my stopwatch. And then after about 10 minutes, I'll stop it, and I'll see, oh, how many counts there is. So everything comes down, right, even though I said it's 1 disintegration per second, right, typically we look at how many counts in a minute, right, or counts in a second. Most of the time, if I'm not wrong, most of the questions, right, goes in terms of minutes. So you would look at counts per minute. Wow, bad handwriting. Let me do it again. Counts per minute. Okay, could be counts per second, but typically it's counts per minute. Okay, so every time you want to find out any measurements with radioactive sources, right, you need to first know the background radiation. Okay, why is that so? Well, that comes to the next part. So this is the part, right, where it becomes mathematical. This is the part where we start looking at your graphs. Okay, it is also the part which you can easily score, but you need to know very clearly if it is a type 1 or type 2 question. Okay, so in all these graphs, let me get to it again. In all these graphs, we are actually trying to find out or understand this concept of half-life. Okay, now with the concept of half-life, with the concept of half-life, right, we also need to ask ourselves, right, does my graph consider background radiation or not background radiation? What's up, Titi? Say hello? Say hello.
Hello.
Okay, give me a moment. Okay, where we are now? We are at page number 328. Okay, so I'm deviating a little bit from the textbook because I want to make this a bit clearer in terms of thought process. Okay, so we understand half-life because really if you want to understand radiation, we all want to talk about emissions and stuff like that, right? So what is a half-life? A half-life is basically the time taken, right, for half that nuclei to decay, right? So whatever I have, how long it takes for half of it to just decay, right? So we have many different types of nuclides, right? All these different nuclides which are radioactive, how long for half of it to decay and becomes half the amount? Okay, so if let's say, right, I have this item, so let's say I have this thing over here, and this has radioactive nuclides inside, right? How long for me, if I were to use my GM counter, so I have my GM counter over here, my GM counter, and I put it close to it over here, right? And I have a certain reading. Let's say that reading at first is 900 counts per minute, right? Let's just say. If half of them decay, it means, right, that I'm going to get, well, 450 counts per minute, right? Counts. Because, well, for half of it died already, in a sense, not really die, okay, decay. So how long does it take for that count rate to drop by half? That is my half-life timing, right? So it is time taken for half the nuclei of the nuclide in any sample to decay. So that's half-life, right? That's very, very important also when we understand radioactive stuff. How long does it take for it to be less radioactive? Because I don't want to have all that radiation coming to me. I want to know when it's less radioactive. So when it comes to half-life, we can actually see it in a graph. Okay, so for now, we're going to ignore, just for a little moment, my background radiation. So we have graphs to draw for all of things which are radioactive. So let's say, for example, if we look at page number 329, we have a picture of iodine-131 atoms. Okay, and now let's look into it also. Okay, so this is something that's radioactive. When I start counting, I realize that, oh, wow, it is at 120, okay? 120 in the millions. And I want to find out, right, how long it takes for it to go from 120 to 60. In my graph, it shows me that it took a total of 8 days for it to drop from its original amount to half its amount. So that's one half-life. Now, is it going to drop by 60 again? No, half of it. So from 120 to 60, that's one half-life. That's 8 days. If 8 days is half-life, that means the next half-life, also another 8 days, will drop it by half. Again, it doesn't minus 60, it divides by 2, half. So from 60 to 30, and 30 to 15, and so on and so forth. So if I want to know how long it takes to get from 120 to 15, I need to take the number and half it, and half it, right? So I can see how many cycles it takes, how many half-lives it takes to drop to a certain number, okay? So in this case, let's do it this way, okay? Let's write out it as clearly as you can. The idea is this: it has gone from 120 BQ, right? And then I know it takes one half-life, right, to drop to 60. Now another 8 days, that's going to drop to 30. Another 8 days is going to drop to 15 BQ, right? How many half-lives are there so far, right? So I'll see over here, it's a total of 8, 16, 24 days, and that is worth 3 half-lives. It takes 3 half-lives to go from 120 to 15, right? So how do you use this kind of idea? So let's say, for example, if you look at your textbook, right, it's a work example. It tells me that I have a certain sample X. Okay, now sample X is radioactive, and I've realized that how much radioactivity does it have? It has a count of 600 becquerels, right? But here's the thing. I know, okay, it's given to me, right, that the half-life of this thing over here is only going to be 6 hours. Okay, so I would like to know what is the amount of radioactivity after 18 hours, right? So the question is, after 18 hours, what is the amount of radioactivity? So how many BQ, right? So we start the working again. So 600. Right? After 6 hours, it will be halved, so it becomes 300 becquerels. Okay, so I have 18 hours to go, right? So how do I get to 18? So 6 and 6, that's 12 already. That brings me to 150 BQ. And I think I need to do one more, correct? 6, 12, 18, correct? 6 hours. That brings me to 75 becquerels. So let's check. this over here is a total of 18 hours. 18 hours. 6 of 18 hours. After 18 hours, I have 3 half-lives. And I see that it has become 75 becquerels. So my current amount of radioactivity is 75 becquerels. Let's take a look at an example from the textbook, shall we? Oops, what did I do? Let's take a look at the example over here. Alright, so in this example, we have this curve. Now this curve shows, this is the decay curve of a radioactive nuclide, right? So from this curve, can I find the half-life of the nuclide? So here's the understanding. Let's see. When time is 0, my count is 9,000. So I need to find out how long it takes to go from 9,000 to half of that, which obviously would be 4500. 4500 is between 4,000 and 5,000, so it's here. So from here, 4500, typically, right, if you are doing exams, right, you go like 4500, you put over here, and after that you dot across and see, okay, so that's where it's 4500. What's the time take, how long did that take to get to 4500? And over here you say, oh, 3 minutes. So it means that the half-life of this nuclide is 3 minutes, correct? Makes sense, right? And it also shows, right, that if I want to go half of that, 4500 divided by 2, what's that give you? This one calculator. 4500 divided by 2, that's 2250, right? Which means, right, at the next cycle, right, at 6 minutes, I should have 2250, and right? So it is, right? 2250, that's 6 minutes, right? So using a curve like this decay curve, you can also read what's your half-life. Now, that's fantastic, correct? But there is a problem, isn't it? Because it seems to tell us that so that's my radiation of this item. But we must also remember that every time we measure any form of radiation using my GM counter, right, I will also have background radiation, correct? That background radiation that comes from other sources which I didn't have any control of, is there, right? Which means, right, it's going to add to it, right? So this is kind of like type 1, where the question doesn't tell you anything about background radiation, right? This doesn't happen very often. Typically, they'll give you type 2, where inside the graph, you're supposed to figure out that there is background radiation too. But how do I calculate that? So this is going to be the final part of this subtopic concerning measuring radiation. Afterwards will be the hazards. Okay, so we're on to the last part already. Okay, but as far as this lesson is concerned, we're going to stop it here. Right? The next video will be about how do I find the count when there's background radiation involved as well. Okay.